And we just had a very, very busy week with a major international conference that we hosted in Auckland, and that finished yesterday at 2 p.m. So we can't believe it's Monday. But as a positive side effect, we have all these esteemed speakers in the country who we convinced, instead of sightseeing, we convinced them to come and visit Auckland instead. So we're very, very fortunate. And it's my pleasure to have two speakers for today, not one, but two esteemed researchers, and I'll introduce them in order. First, it's Professor Dr. Maike Schindler from the University of Cologne. Mm-hmm. And Maike has trained as a mathematics teacher and a special education teacher. Now, let me just mention for New Zealand colleagues, to become a teacher in New Zealand, I'd say it's equivalent to a master's degree in pure mathematics and applied mathematics at our level. So you have to be very much skillful mathematician before you can be qualified as a teacher in Germany, as far as I know. After working as a teacher for 5 years, Maike enrolled in a doctorate program at TU Dortmund University and finished her PhD in 2013 with a distinction. After that, she held substitute professorships at the universities of in Hanover and Bochum. She also been a postdoc at Örebro University in Sweden from 2014, and that's where she met our second speaker, Achim, that I'll introduce later, and they began to work on eye tracking research in mathematics education. Maike has been started as a junior professor at the University of Cologne first, and has been promoted to full professor since 2021. And she's specializing in mathematics and special education and inclusion. Her research focuses is quite broad. It consists of learning difficulties in mathematics, mathematical creativity and giftedness, mathematical problem posing, and theories in mathematics education, as well as eye tracking and AI in mathematics education research. She is a member of the editorial boards of several journals, including one of the two top journals in our field, which is Educational Studies in Mathematics. And she is been busy guest editing a special issue on the emerging technologies in mathematics education research in ZDM, and also a special issue on eye tracking in maths ed research in ESM, which will appear by the end of this year. Finally. We'll believe it when we see it. But
yes, exactly.
And since 2024, Maike is a senior editor in IJSME, which is International Journal of Science and Mathematics Education. Thank you, Maike. And I'll introduce our second speaker, who will take over midway from Maike. Professor Achim Lilienthal is a professor of computer science at TU Munich, Germany, where he leads the chair of perception for intelligent systems, and he is also a manager of the AI factory at the German Technology Museum in Munich, and he's a guest professor at the University of Örebro, Sweden, where he established the Mobile Robotics and Olfaction Lab and two spin-off companies, Reti Nua and QTPI. His core research interests are in perception systems in unconstrained dynamic environments, and various research topics, including human-robot interactions, eye tracking and AI support systems, and mathematics education research. So Achim's interest in the maths education research was sparked when he met Maike at Örebro University in 2014. So it's kind of a joint effort in a way, and that's why it makes sense that they present together. Achim started studying physics and obtained his PhD in computer science from Tübingen University with a thesis about gas distribution mapping and gas source localization with mobile robots. He has published more than 300 refereed conference papers and journal articles, has co-edited several special issues, and has served to the community in various roles. He has been PI in 10 EU projects and coordinated 3 of them. And also he supervised 43, or has been supervising 43 PhD students and mentored 30 postdocs. This is an impressive track record, and I'm delighted that Maike and Achim could be here to present their research to us. And please welcome Maike and Achim. The floor is yours.
Thank you very much, Tanya, for having us. We are really honored and pleasured to be able to have that talk today. And I will start right away because we do have no time to lose. Today our talk is about using AI together with eye tracking in mathematics education research. And we want to give you some insights into some studies where we applied AI on our eye tracking data, where we wanted to investigate student strategies. So before we start, I wanted to give you some illustration of what we're doing. Here you see a representation that we use very often in Germany for kids in order for them to learn the numbers, develop a number sense for numbers up to 100. So here you can see 100 of these dots, basically. I don't know whether you have these machines here as well, or whether you have seen them. Well, what is important to know is that all the dots on the left side count, and all of those that you push to the right, they don't count. So you just need to count how many dots you see on the left side, all right? So that is a question that we pose to kids when we assess their math abilities, for example. And now you can see a fixation star. And we ask the kids to look at that in between the tasks. And now I show you the representation again. And I want you to, as fast as possible, count how many you see on the left side and then just say the number. Okay? Great. 89, exactly. So you were quite quick. How did you see that? Yes, exactly, right? You saw that one is missing here and maybe one line is missing. 99, I heard some kids do that mistake as well, because you see one is missing. Can you imagine how many kids proceed in that task? Because that's quite a skilled strategy, really good. But what do other kids do?
How much time did they have?
Well, as much as they needed. Some of them, it takes them, I don't know, a minute. Exactly, counting one by one. We see that, actually. Even though they know the representation from the mathematics classrooms, they count one by one. And many of them also count the rows, right? They count the rows. And so I'll show you a video, an eye tracking video. And what you can see is the green dot, which is wandering around. That is the student's gaze. Yeah, that's the eye movement, okay? I'll just show you. Inhaling, exhaling.
89.
89. So what did that kid do? Do you have any idea?
Counting tens and counting ones.
Exactly, right? So it counted the tens and then the ones, interestingly, from right to left. And then inhales, breathes out, and counts again. And then says correctly 89. And we've seen that quite often. This is a good example to show what eye tracking can give us, right? People always ask, like, can you really see something in eye tracking? Sometimes you can, yes. It depends a lot on the tasks. Imagine you have an arithmetic problem. I will pose you like 12 plus 37. I wouldn't see much in your eye movements. Right? It wouldn't say much about what you were mentally processing. So it depends a lot on the task, and this is why we always try to advertise that we need domain-specific interpretation of eye tracking data. You cannot always say that a fixation means this or that. We need to domain-specifically design our task and also to interpret the data. are some heat maps. Heat maps show, like in warmer colors, where the kid looked at more intensely for a longer time, and greener colors where there were not so much gazes. And here, that is the heat map from the kid that you just saw, a kid with mathematical difficulties, actually. And this is from 2 other kids without difficulties. And here you see that kid basically looked at that line, also at the missing dot, and a little bit to the right to double check, right? And here that kid looked predominantly on that missing dot, and then also knew 89. We'll come back to that later. So why are we using eye tracking and AI? Well, as mathematics education researchers, we see that it's important to not only evaluate the achievements of students, their results and their products, but also to look at their thought processes in any way that we can and their individual strategies. There has been a recent progress in the use of eye tracking, the recording of eye movements in math education research, and many researchers have seen that it has a lot of value for analyzing student strategies in different mathematical areas, including enumeration, quantity recognition, number line estimation, and so on. And as I said, it requires a domain-specific interpretation for gaining meaningful insights, qualitative insights into student strategies. Some people tell me, well, Maike, in that talk you said that in number line estimation or in enumeration, you said that it is meaningful, and in geometry you said that it isn't. Yes, that's just true. Yeah, you need to look into what kind of task you're dealing with. And as a side remark, before we conduct a big study with a lot of students, we always tested. We first tested with our colleagues on the same corridor. Then we tested in a pilot study with some kids, because eye tracking data is really sensitive towards anything that you might misdesign or design a little bit like you didn't think about it so much. And then the gazes are drawn to that direction, so you need to be really careful. The analysis of eye tracking data, which are rich by nature, is time-consuming and demanding. You can imagine that analyzing these videos takes a lot of time. And this is why we saw the need for more efficient methods for the analysis of student strategies with bigger numbers of students. I'll show you one paper later, one study, where we had thousands of these videos. And it takes a lot of time to analyze them. And there we thought, using these heat maps and putting them into a machine, Achim has better words for that, putting them into a machine and let the machine analyze them or pre-analyze them for us, and suggesting a categorization to us that we can then qualitatively analyze, that would be a good way to deal with that large amount of data. And this also offers the opportunity that the AI can provide new perspectives on the data, and also gives us opportunities for new discoveries. So, a little background on eye tracking. I'll do that real fast. This is the human eye. In the back of the eye, we have the fovea centralis, and this is the point where the eye can see sharply. When the light enters the eye always needs to move so that the object that I want to see sharply is projected onto the fovea. That means basically that my eye always needs to move to whatever I want to see sharply, and this is what we are tracking in eye tracking. So what a camera sees, this is a picture I took some time, it looks like that everything is sharp. What an eye sees is we see sharp what we focus on, and the rest is actually blurry. If we want to see something sharply in that corner, we need to move the eye there. And that is also interesting. The visual field is approximately 180 degrees to 130. You can test it ourselves, and I want to invite you. So put your arms here and wiggle a little bit with your fingers, and then you can test how many degrees you still have, because it decreases. So I want to think that I still have 200 degrees of visual.
Is this just looking straight, or just by looking straight?
Just looking straight. Yeah. Okay. And, and in height is about 130. However, the foveal vision, what I can see sharply, is only 2 degrees times 2 degrees, which is a thumbnail size in an arm's length distance. So that is not so much, right? So if you want to see, if I look at Achim and I want to see Tanya sharply, I need to move my eye there. Today, video-based eye tracking is common. So we have basically 2 different devices that we can use. One is screen-based eye tracking, where you have such a black bar that you put onto a monitor. You just click it to the frame of a monitor, and this then tracks the student's eyes. And we have eye tracking glasses where that the kids can wear, which I also actually used also in front of the screen. The video that you just saw was from eye tracking glasses because you still saw the surrounding of everything. Advantage is that you also can see where the kids point at because you see everything, and it's also synchronized with audio. Yeah, so what the kid, how they breathe, that we could also hear. Otherwise, we wouldn't have heard that. And it all comes with some software that helps you creating these representations, the videos, the heat maps, and everything. Some years ago, eye tracking was still conducted like that, where they put glass contact lenses into the eyes with some cables, and this is how the eye movements were measured. Yes. But nowadays, with kids, we're just doing infrared eye tracking. This is not harmful at all, yeah? Just for you to know. This is from one study that we conducted actually in Cyprus, a beautiful country. In Cyprus in the last October, yes. And with a new eye tracker, this is a really small one. And you see there's a lot of devices. It is also screen-based. That means it's static, and here you can see that it's a kind of MacGyver solution to some issues with the eye tracking, because we wanted the kids to work on an iPad, and what we didn't know and what the manufacturer didn't know is that the eye tracker needs to have a minimum distance from the eye. Yeah? And normally, it all comes with a stand. You have the eye tracker, you have the device, well, let's say a tablet computer, an iPad, or whatever. And only because we're working with small kids in grade 1, their arms are too short. Yeah, so whenever they touch it, it's too close. Yeah, and then we needed to build this thing so that the eye tracker is behind the tablet computer. These are things that the manufacturers, of course, don't think about when they develop their devices. So, how does it all work? The eye tracker, the person looks at a screen. The eye tracker then sends out an infrared signal to the pupils. It captures the reflection of the infrared light on the cornea in the eye, and it determines the difference between the position of the pupil and the reflection of the infrared light on the cornea, and thus calculates the position of the gaze. And this is how it all works. And here at school, with this eye tracker, a Tobii eye tracker, which is clipped onto the frame of the screen, it has infrared, but infrared light you don't see it. You just see it through the camera of my mobile phone here, but otherwise it's not visible. So it doesn't distract. And it works actually the same with the glasses, where the person looks onto an object. And here we also have these infrared illuminators that illuminate the cornea, and we again determine the difference. So it's actually the same technique, only that these infrared lights are in the glasses. Yes. What we always need for eye tracking to work is a calibration, or what we always needed. So that means before a kid or a student starts working on a task, we need to calibrate the system to that particular person. this often looks like that. You have some points on the screen, the person is asked to look at them, and then the system is ready to go for that person. Nowadays, there are also systems that don't need to calibrate for every person, so it's pre-trained models. But we need to be aware if we conduct studies with small children that they are now trained for small eyes. Yeah? So the accuracy drops a lot if we have children that we're working with. And the accuracy for screen-based systems is better than for glasses. For screen-based systems, my experience is that they have 0.8 degrees on average or 0.9. The manufacturers say something different, but this is my experience. And the glass is about 1.5 degrees. This can be increased by stabilizing the head, which I don't do, but there are chin rests, for example, if you have reading research, and there you need a really good accuracy, and most of the times then the heads are fixed, but we can't do that when we work with 6-year-olds. But the accuracy plays a real big role also for the design of the task and for the interpretation of the data. Well, if a person is sitting in front of the screen, which is mostly approximately 60 to 70 centimeters, and we have an accuracy of 1.5 degrees, for example, 1 to 2 degrees here, then this is on the screen, you can do the maths yourself, about 1 to 2.5 centimeters. Yeah? That means that objects that are important, that I want to, where I want to investigate whether the kids are paying attention to them, they need to be away from each other, 1 to 2 centimeters, so that I reliably can say onto which object the person is looking, right? So I need to anticipate a little bit how big will the accuracy be and how shall I design my tasks. Yeah? Yes. And this is a chin rest, as I just mentioned. Yes. And of course, then the kids or the persons cannot write or do anything, right? They cannot point because it needs to be fixed. To show that difference, so this is approximately 1.5 centimeters. This is 1.5 degrees. This is approximately 0.4 degrees. Here you see that for doing reading studies or mathematics education, word problems or whatever, you need a real good accuracy if you want to say something about where the person looked at in the text. That is really tricky. I always tell researchers in mathematics or science education, if they want to do word problems, then they need to orient themselves in the reading research area. And they have eye trackers who are much, much more accurate, much, much more expensive. They don't have 120 hertz, but 1,000 hertz, and they need chin rests. So reading is really a difficult thing when it comes to eye tracking. So there's growing interest in the use of eye tracking in math education. It has already been used for 100 years, but initially mostly in cognitive psychology. And the strong research, the strong increase in the recent years has been caused by different factors, one of which is that eye tracking systems are more accessible and that little technical know-how is required. You can use them quite easily, and eye tracking devices are becoming more affordable. At the same time, of course, the global access is different and the opportunity to participate in that kind of research because, of course, not everyone can buy the systems as easily as we can in Germany and probably also in New Zealand. Here's a little bit of an overview, and to summarize all of it, eye tracking research in math education has been dealing with a lot of topics, numbers and operations, geometry, patterns and functions, data and chance. It kind of covers all the contents that we have in the curriculum, and we recently analyzed that again, and we found that the curriculum is pretty covered, so that it's really nicely distributed through eye tracking research nowadays. And also, eye tracking research looks at mathematical processes, for example, proofs, problem solving, word problems, mathematical reasoning, and so on. If we want to analyze eye tracking data, we can do different things. And what I just showed you were videos, which is a dynamic scan path visualization. These things here, gaze plots, they plot the gaze as well, but it's the static gaze path visualization. Yeah, here it's basically the same thing, only that the circles and the numbers within the circles show where the kid looked at, what the person fixated, in what order. It's a directed graph, if you will. And then we have heat maps that I already showed you. And then, of course, we have these measures like fixations. That is the moment where the gaze stands more or less still on a certain point, normally defined to be like a fixation is between 200 and 300 milliseconds. We have saccades, which are the movements from one fixation to another fixation, dwell times, and many more. And they are very often analyzed in different areas of interest. And then the people compare, like, did the kid fixate more onto one area of interest or the other? You can define them on the screen and so on. What we have been doing in the last years is that we analyze student strategies, and we published it in some papers. Here you already saw one example, the video of the student with math difficulties counting the rows and the ones. And here you see another example, a number line, 80 on the number line. I will show the video again. And what did that kid do? Exactly, yeah, exactly. It counted all the hedge marks. And here you can see the heat map belonging to that scan path. And this is what we also use in our studies. And now it's Achim's turn. I just give you the mic.
Okay, then just. All right. Oh, that was far too loud. Sorry. Now everybody is awake again. So I want to tell you now a little bit about my side of the work, or where I can come in. So this is that we try to use artificial intelligence because we unfortunately don't have as many experts as are needed. And also, these experts are maybe not as good, or it takes too long to educate them. So I have never been a teacher myself, but I have seen some of these videos, and I can see the strategies. And what you have seen so far, these are the very clear examples. Now, if I try to code them and look, what strategy is that, then it will take some time. But if Maike does it, then it's like she looks at it, strategy 1, she looks at just the beginning, oh, this is strategy 3. And so she's really fast, but it's hard to imagine a situation where we have enough Maikes to do that. So what we want to do is we want to use artificial intelligence, which is actually a way of programming computers to do human tasks so that they would take over and that they can do what we can do and sometimes more, that they sometimes can tell us, here is a structure in the data that you might not have seen yet. So just because there's a lot of discussion at the moment, just a little bit an outline of the landscape. So there's artificial intelligence. These are basically approaches that are being worked on, being discussed since the 1960s. And that is roughly following some definitions is these are ways to teach computers, to enable computers to do what humans do as well. Decision making, for example, or categorization or something like that. A subset of it is machine learning, and that's what we talk here primarily about. And machine learning, that is basically done in two different ways, which I will explain in a second. What you might have heard is the next, so the machine learning is a subset of AI, and deep learning is a subset of machine learning, and deep learning is maybe something that you have heard about. So this machine learning is all sorts of ways to make the computer learn from data, and deep learning uses specifically neural networks that have many layers. And this only became possible because of the development in graphics cards. Maybe some of you have heard that NVIDIA is now is actually as valuable as the whole German stock market, because they are providing these graphics cards that drive the AI revolution. And what people are talking about nowadays, this is efforts of OpenAI and so on, is called generative AI. That is large models trained on all the text in the internet, or large foundation models trained on text and other modalities. So we are primarily talking here about machine learning, because you can actually say that these are all subsets, but if you go in this direction, it also gets harder and harder to say what they really do, what these models really do. So people at OpenAI also don't really understand everything that their models do, and we try to keep as much as possible an understanding. We try to figure out a way that the artificial intelligence might be able to tell us something that we didn't see, but we want to be able to identify then why did it tell us. So machine learning, and I read this definition here, is a set of methods that allow us to do automated analysis of data. And to do that so that we can automatically detect patterns which we might have seen or might have not seen, and then use that in order to predict future data, to make decisions, and this all under uncertainty. So we have seen some examples where it immediately strikes us what the children are doing, but this is not always the case. And so we have, in this level, we have three important classes of this machine learning, and one we can forget about immediately, which is reinforcement learning. So we are talking about supervised and unsupervised learning. And what does this mean? For supervised learning, I have to show the computer an example and give it the direct result. So I show the computer, for example, an eye tracking heat map, and I say, and the child did this strategy, or the child was in need for like extra support. And then the computer can learn to make this distinction. Or unsupervised learning, which is actually, so supervised learning, I already explained that, and we will actually see that in one of the examples later on. So I have heat maps, and these heat maps are heat maps of children with math difficulties. And these are heat maps of children that do not have math difficulties, that are typically developing. And it's really hard for us in general to distinguish them. There may also be a gray zone for whom we cannot properly say. And then we have some machine learning magic, which I won't go into detail. But then I throw in all these heat maps, and then it can try to predict. And here you can be sometimes quite successful and predict something from this data that is actually quite far-reaching. So you might be able to predict whether the child needs extra support. So this is the supervised learning. So for each measurement outcome, for each heat map in this case, I need to exactly say what's the result. But I can also go for unsupervised learning, and unsupervised learning is more or less the question, computer, here you have lots of heat maps, where do you see similarities and where do you see dissimilarities? And that is a very ill-posed question. There can be many different ways of seeing similarities and dissimilarities. So there's always an element of trying. And I just want to say, so this is called clustering, and I just will at the end will say what in this clustering are the important dimensions that we have to work with. And so here I want to show a pipeline of how we work with the data. So first of all, there's eye tracking, which leads to such a result. And this is eye tracking of some children that worked on number line tasks. So we've seen this before. and then we do some data pre-processing, because if we have inaccuracies in the eye tracking system, this sometimes leads to wrong interpretations. So we have a way to identify, more or less by knowing where the children most often look at, to go from here to there. Then the different eye tracking results look more alike. So we call that remapping. And then we actually selected some unsupervised learning methods, clustering, and they then tell us you have, for example, here you have 10 different heat maps, and they are similar to each other, and they are very dissimilar to that one, but they have a sort of similarity to that one, and then we try to interpret these data. So it's basically the computer acts as a colleague and tells us, I see similarities here between these children, and I see dissimilarities between those children. That, of course, could also lead to a situation where the teacher, after such a test, has a better knowledge of how the classroom is composed with respect to this particular task. Okay, and then we try to do, so this is actually a very nice example from Maike about the ill-posed character of clustering. So what we are doing is we tell the computer, what clusters do you see here? And it's a valid answer to say, well, I see the different colors. But it's as valid to say, well, they have different shapes. Or, what was the?
Different properties, like some of them are curved, some of them aren't.
Exactly. So all of these are, so to speak, correct answers. And therefore, we need to try out different clustering algorithms. And these different clustering algorithms can actually differ by ways of how I compute similarity or what clustering algorithm I actually use. So the rest here is that we try to understand what these different clusters mean by computing, for example, the average heat map, so a representative of this class. And then we then can say, well, this is clearly a child, or these are clearly children that count. And then we do some analysis with that. So this is one way that we go about in our research. So either we try to directly give the output that we'd expect from the computer, or we ask kind of as a colleague, what kind of structure do you see? And I think I explained this already. So these are the two dimensions of clustering that we look at. So first of all, how do we measure distances between different heat maps? And second, what clustering algorithms do I use? So.
Okay. All right. Okay. About the studies. Can you hear me? Yes. About the studies, they come from two projects. To give you some context, this is one project, this is the other, to make it very quick. So it's always projects where we use AI in order to develop digital learning systems for the kids. One is in grade 5, one is in grade 1, and it's all projects that are funded either by the Federal Ministry of Education and Research in Germany or by the EU. And in one of the projects, we are working together with also colleagues from Cyprus. This is where we conducted the study that I just mentioned. I will not go into detail because of the time. Oh, well, one aspect that is really important and really cool, I think, is that we're developing an app in that project here, Madita. And that project develops an app to support kids in their mathematical abilities in grade 1 throughout grade 1. So it's when they start school, they play with the app with different task types, and then the teacher gets an overview of all their kids and sees how they develop, and they get to support at their level, it's adaptive, and so on. And we develop it also in sign language, which is really cool because these kids are struggling so much at school. Nobody knows really why, because their math abilities are actually not that bad, and the prerequisites are actually there. So that's really cool. But we don't have time for talking about that now, maybe later. So the first study, as I said, it's about strategy use, and we're using unsupervised learning and AI to suggest strategies to us based on the heat maps of the kids here in number line tasks. So the number line is an important representation. You probably know that it's used to support the development of math skills and to foster number sense. And kids are struggling with the number line. If we're conducting studies, they always say, oh no, the number line. It's almost as unpopular as the clock. I don't know if the clock is really worse, but the number line is directly before. The number line is bad. And we conducted this study in order to support kids with math difficulties who have difficulties in understanding basic arithmetic concepts. And these difficulties are typically apparent already in primary school, and they often persist into secondary school level. And these kids also very often have issues with the number line because, of course, they have issues with the number sense. So our question was what strategies the kids have for locating numbers on a marked number line. It was in grade 5. And if and how kids with math difficulties differ from kids without such difficulties. We had 140 grade 5 students with a mean age of 10.6 years, and 42 of them had mathematical difficulties, 62 didn't. So what we found using our clustering algorithm, that there were basically 4 strategies. And this is how the data were clustered. We used the heat maps, as I said. And what we found was that there was either like the direct orientation, for example, here for the number 40, so the kids could look more or less directly at the target number. Strategy 2 was that the kids oriented themselves from the beginning, like here for 70, counting like probably from 0 to 70, even though in the heat map we don't know. It could be that the order would also be that in that direction because there's no order in the heat map. The orientation from the midpoint, here from 70, and the orientation from the endpoint here for 800 on the number line from 0 to 1000. So these were the 4 strategies that we found using our clustering algorithm. And this is actually how it looks like for one number, which is 40 here. So we had these clusters. It was 3 times 4, that means 12 clusters. 4 of them remained effectively empty, and the others were filled. You can always see how many kids were in the clusters. For example, 19 here, and 8 of them did have mathematical difficulties, and 11 didn't. Yeah? So we let the machine cluster, and then we already knew what kids had the difficulties because we conducted an extra test with the kids. And these are the average heat maps per cluster that we let the machine create. And what we then did is that we qualitatively assigned strategies to these clusters. And so this is what we as human experts, basically my PhD student Anna, Simon, and I, what we did. And here you see the strategy 1, which is more or less a direct orientation. Here the strategy 2, which is the orientation from the beginning. Here you can see that quite clearly. And this is strategy 3, the orientation from the midpoint, whereas the orientation from the end didn't occur for the 40. So regarding the group differences, yes, we found significant differences in the use of strategies between students with and without difficulties. And in particular, the students with math difficulties used the orientation from the beginning more often than students without such difficulties. And the students without math difficulties used the orientation from the end point more often, which is not totally surprising to us, but it was anyways insightful and can be used to design the support for the kids. Now the study 2, very quickly. It was about the small number enumeration processes of deaf and hard of hearing kids, where we also used eye tracking and AI. Regarding deaf or hard of hearing kids, we know there's the so-called math gap, that at primary school age, deaf or hard of hearing kids already show a developmental delay of about 3 to 4 years. And at secondary school age, the delay gets even bigger. Less than 50% of the deaf or hard of hearing children can count to a level that would be appropriate for their age. Here we looked at the enumeration of small numbers, and we wanted to look into the processes as well and to see if and how students who are deaf or hard of hearing differ from kids who are hearing. We had 164 hearing kids and 63 students who are deaf or hard of hearing. That was a massive data collection. You can imagine there are always a few kids in each class, so there was a lot of schools involved in that study. And here we also had clustering and 3 types of strategies. The simultaneous enumeration, which is basically looking at it once and seeing. For example, for the dice 5, you can just recognize it. It's a picture, right? You don't need to necessarily count all the dots. Then we had the use of structures or symmetries as number 2. And the counting everything, basically. So when the kids counted every dot, or at least more of half of the dots. So these are the 3 strategies. What we found was, yes, the kids differ, and they differ basically in 3 out of 4 kinds of tasks. So they differed for subitizing, they differed for counting randomly arranged objects, they differed for dice pictures, but not for the beyond dice range. This was the only one where they did not differ. But the kids who were deaf or hard of hearing were always better. And that was quite cool because they are performing so much worse in mathematics everywhere, but not in this case. So it was really good to see that the kids who are deaf or hard of hearing, they used the simultaneous enumeration more often. And you can see that as well. And the others, they used the use of groups and structures more often, but they looked at more things. So the kids who are deaf or hard of hearing were actually faster in grasping the numbers correctly. And this was also the case for the dices. And here you can see also that they counted all items less often. So these 3 kinds of arrangements were all significant, which was a quite cool finding. And we had a couple of 1,000 processes which we would never have analyzed because we all have a lot of things to do. We would have never received that result if we hadn't had the AI to analyze the data for us. And now let's go into the discussion. Achim, quickly.
Very quickly.
Maybe you can use the mic there.
Okay. So I hope you can hear me also quite well from here. I want to conclude the talk by summarizing a bit what our conclusions are. So conclusions when using artificial intelligence and eye tracking together, and especially in the case to identify student strategies. So the most important message, take-home message, I think, is that this is really a powerful combination and that we are really only at the start. Especially what we are seeing is that we can use AI already in research. So AI can help us to analyze more data, and AI can support us as a researcher colleague. So it might be able to show us, well, here's a strategy that you might have overlooked. Here's another class which seems to be very different from what we have seen so far. And that's really nice in helping us as researchers. Then the second very clear case is where it can actually learn from our expertise and bring that into a larger scale into the classroom. So where we actually say, here, that's how a certain strategy looks like, and that's how you can recognize it. And in order to avoid that we have to train massively teachers, we can outsource this to computers. And third, eye tracking devices are some eye tracking devices are actually very expensive. So one direction that we are following is, can you use just a webcam on your computer to do the eye tracking for you? Then everybody can do it. Every school can afford it. And this is possible, but you pay for it in terms of accuracy. So it's not as good eye tracking as with a dedicated device. But you can also use some other techniques from artificial intelligence to get better there. And so that there is a hope that you can actually offer this to many schools. Finally, we want to point out that in our work, we always try to keep things explainable. Because AI, if you look at the best examples where it's actually the most impressive applications, it's best in the information space when there are people who select the good results. One of the applications that I like most is coloring old pictures. These are my grandparents, and I've never seen before the picture with colors. And so this is great. This is my grandfather. This is him in colors, and I feel much more closer to them than I ever did before. But this is me playing handball, and here it just didn't work, right? So in the end, I'm talking about the pictures on the right because I'm amazed by them, and I just throw away the example on the left. And in order to be able to do that in a larger context, we need to have ways that we can explain this to people. Here I just jump over this. So we want to have what's written on the right side, preferably explainable results, so that actually the computer as a colleague to us as researchers can, like that the result is still explainable. That's why we, for example, stress the fact that we have these average heat maps and that we can look at them and try to reason what that means to us. And ideally, it would be that the AI analyzes the students, but then communicates with teachers in natural language. And then, of course, generative AI can play an important role. Final remark, the combination of eye tracking and AI in mathematics education, we believe, is very much at the beginning. A lot of what you can do is uncharted territory on a map that we just don't know where it will lead to. And therefore, we started in 2015 to really work together on this, and we are still amazed. Thanks very much.
We've got a couple of minutes for burning questions, and then we will take the speakers to the Old Government House for a coffee or a drink, and so you're more than welcome to join us if you want to ask more questions afterwards.
Thank you very much.
Sorry, Al.
Yeah, just one. So you've got some results with regard to the strategies, but how do you use it? How does that help you to actually improve the children's mathematics?
So, well, let's take the number line example. Then we know that the kids are counting each hatch mark, which is not the desired strategy. We want the kids, for example, to use structures of 50, or on the abacus that you saw, also there, we want them to use the structure of 50 or the structure of 100, for example, for the 89. So once we know what the strategies are, we can give them adaptive support. One of the projects, Achim, can you open the slide, please, again, with